This is the synthesis of digitoxigenin. Digitoxigenin is a cardenolide which is an aglycone of digitoxin, an extract from the purple foxglove plant Digitalis purpurea. It has been examined as for use as an anti-tumor compound. Here is the UPAC name and the article reference. The first reaction is the Mitsunobu reaction, where this molecule here will react with triphenylphosphine, diethyl azo-dicarboxylate, and trifluoroacetic acid here. This will remove the alcohol and will be replaced by a nucleophile with inverse stereochemistry. The mechanism starts by triphenylphosphine making a nucleophilic attack. The lone pair of electrons in the phosphorus will attack a nitrogen, while the double bond between the nitrogens will break. This gives a positive charge to the phosphorus and a negative charge to the nitrogen. The negative charge will deprotonate the alcohol and will form an alkoxide. This alkoxide has a negative charge, and this will be lured and trapped by the positive charge in the phosphorus. Then after that, the phosphorus will leave the dead molecule and attach to the oxygen right here. In the stage 4, the negative charge in the nitrogen will deprotonate the trifluoroacetic acid, activating this nucleophile. And then finally, in this stage, the trifluoroacetic acid, which is the activated nucleophile, will attack the electrophilic carbon, while this part will live as a leaving group, as it is a very good leaving group, as the oxygen is very activating, pulling electrons towards itself and the cation part. This is an SN2 reaction which has the inverse stereochemistry as the nucleophile, because this nucleophile will do a backside attack, changing the stereochemistry. Second reaction is a modified Horner-Wadsworth-Emmons reaction, where this molecule here will react with the phosphonate group here, and in which the butyl lithium will act as a base. All of this to remove the aldehyde here and form a cyclic ketene dithioacetal. Step 1 of the reaction, this butyl lithium will act as a base. Its negative charge will remove the hydrogen of this carbon here in the phosphonate group to give a phosphonate carbon ion activating this nucleophile. This activated nucleophile will attack this carbon with partial positive charge, and so there will be an addition from the carbon ion onto the aldehyde, while this double bond carbon to oxygen bond will break, giving this oxygen a negative charge. Then here this oxygen will have a negative charge, which will bond with the phosphorus, and this double bond will break. Then there will be a slow step of the reaction where there will be a syn elimination of the phosphate anion, and there will be a fragmentation of the cyclic intermediate, where normally the two bulky groups are untied to each other, favoring an E isomer. Nonetheless, this carbon has the same cyclic substituent, therefore no isomers can be formed. It needs to be noted that normally there will be two isomers as different pathways exist, but in this case only one isomer due to the lack of chirality. The third reaction is the protection of the alcohol by TBS. Here you can see this molecule which will react with TBSCL and imidazole to put this protection group here. The mechanism starts by imidazole doing a nucleophilic attack on the silicon. Silicon has a partial positive charge, so it is an electrophile. This is because the carbon and the chlorine are more electronegative than silicon. This part of the molecule will form, and the alcohol lone pairs will be attracted to the silicon and form a bond. As this molecule has a positive charge, it is very unstable, so bonds will break, and this part of the molecule will leave as a leaving group, regaining neutrality. Finally, this imidazole will deprotonate the alcohol, forming this silyl ether, which is a good protecting group, as it is exceptionally stable in base solution, and in acid solution it is easily removed to regenerate the original alcohol. This video is over, thank you for watching.